15 billion miles from Earth, in a region of space so empty that scientists once assumed nothing could happen there at all, something enormous swept past a small, aging spacecraft. It wasn't a planet, it wasn't an asteroid, it wasn't a ship, a probe, or a rock of any kind. It had no shape, no surface, and no mass you could touch, and yet it was massive. Enough to make the space around it ring like a bell, loud enough for scientists back on Earth to isolate the sound and play it back through a speaker. The spacecraft that caught it was Voyager 1, and what it detected turned out to be one of the strangest confirmations scientists have ever received about what the space between the stars is actually like. Tonight we're going to walk through exactly what Voyager 1 found, how something with no physical form could move through space and shake it like water, and why this discovery matters more right now, in 2026, than at any point since it was first detected. Let's start with where this story actually begins. Not out in interstellar space, but back here, at the Sun. The Sun isn't a calm, steady light bulb quietly burning in the sky. It's a violent, active star, and every so often it erupts. These eruptions are called coronal mass ejections. Massive bursts of hot, magnetized plasma hurled outward from the Sun's surface at extreme speed, sometimes carrying billions of tons of material and moving at over 1 million miles. And at Earth, it can disrupt satellites, overload power grids, and light up the sky with auroras. But most of what the Sun throws out doesn't hit Earth at all. It keeps going outward, past every planet, past the edge of the solar system entirely, into the vast darkness beyond, where there's nothing left to stop it except the thin, sparse plasma of interstellar space itself. And that's exactly what happened in March 2012. The Sun released a powerful coronal mass ejection that raced outward through the solar system. It missed every planet. It kept traveling. For over a year, crossing billions of miles of space no telescope could directly observe. And then, in April and May of 2013, it reached Voyager 1, which by then was already sitting far outside the Sun's protective bubble, deep in interstellar space. Voyager 1 carries an instrument called the Plasma Wave Subsystem, built specifically to detect vibrations in the ionized gas that fills the space between stars. This gas, called plasma, doesn't behave like empty vacuum. It has density, it has structure, and when something disturbs it, it responds, very faintly but measurably. When that year-old solar eruption finally slammed into the plasma surrounding Voyager 1, the plasma didn't just absorb it quietly. It rang, literally. The disturbance caused the electrons in the interstellar plasma to oscillate at a specific, measurable frequency. And that frequency told scientists something they'd never been able to measure directly before, exactly how dense the material out there actually is. Don Gurnett, the scientist at the University of Iowa who led the instrument team, gave this phenomenon a name that stuck immediately. He called it a tsunami wave, not because it was made of water, but because of how it behaved, a wave of pressure racing outward from a single violent event, then washing over everything in its path, causing the medium itself to shudder in response. The exact same way a real tsunami causes the ocean to rise and surge long after the earthquake that triggered it. On Earth, a tsunami can travel across an entire ocean basin and still arrive with enough force to reshape a coastline thousands of miles from where it started. What Voyager 1 detected was the interstellar equivalent. Except, instead of an ocean, the medium was ionized gas, and instead of hours or days, the wave had been traveling for more than a year before it finally arrived. Ed Stone, the mission's longtime project scientist at Caltech, described what happened in a simpler way. He said the tsunami wave caused the ionized gas out a bell being struck. And because the vibrations occurred at frequencies within the range of human hearing, once converted from raw data, scientists were able to release an actual audio recording of it. A rising, eerie tone climbing in pitch, not sound, traveling through air because there is no air out there, but the electrical signature of matter itself shaking in response to a wave that began at the Sun over a year earlier. Listening to that recording, it's easy to forget you're not hearing wind or static. You're hearing the direct signature of a disturbance that crossed a genuinely staggering distance to reach a single, small instrument built decades before anyone thought it would still be useful. That single tsunami wave gave scientists their first confirmed precise measurement of the density of interstellar plasma. And the number surprised them. The plasma density around Voyager 1 during that event was roughly 40 times higher than what the spacecraft had measured while still inside the outer layers of the Sun's heliosphere. Space beyond our solar system wasn't simply empty. It was thicker, denser, and more reactive than the models had assumed. And then, less than a year later, it happened again. In February 2014, another coronal mass ejection from the Sun reached Voyager 1, triggering a second tsunami wave, distinct from the first, rippling through the same stretch of interstellar plasma. Gurnett noted at the time that these events appeared to be far more common than anyone had expected. Scientists had assumed interstellar space would behave like a quiet lake, undisturbed for long stretches at a time. Instead, Voyager 1 was catching repeated traceable pressure waves, each one originating from a specific solar event, each one propagating outward for more than a year before finally reaching the spacecraft and making the plasma ring all over again. What made the second event especially valuable was that it let scientists cross-check their own results. If the density measurement from the first tsunami wave had been some kind of fluke, a one-time anomaly tied to unusual conditions at that particular moment, the second wave should have looked completely different. It didn't. The readings lined up closely enough that researchers could say with real confidence that they weren't looking at noise or a measurement error. They were looking at a genuine, repeatable property of the interstellar medium itself. Dense, reactive plasma, ready to ring every time a strong enough pressure wave rolled through it. This is the part worth sitting with for a moment. Nothing physical crossed that distance. No object, no debris, no spacecraft. What moved through 15 billion miles of space was a wave of pressure, a disturbance passed from particle to particle, entirely invisible, entirely without mass of its own, and yet powerful enough to be measured with total precision from an instrument built in the 1970s, sitting farther from home than anything else humanity has ever built. It's not a planet, it's not a comet, it's not anything with a surface you could stand on. It's a moving disturbance in the fabric of space itself, born in a solar eruption, and detected only because one aging spacecraft happened to be sitting directly in its path. Since those first tsunami waves, Voyager 1's plasma instrument has continued listening, and starting in 2017, researchers noticed something related but different, a much fainter, continuous background hum in the plasma, distinct from the sharp one-time tsunami events, persisting year after year rather than fading out. A team at Cornell University, led by astronomer Stella Koch-Ocker, studied this persistent signal and confirmed that it too reflects real structure in the interstellar medium. Though its precise physical cause remains an open question scientists are still working to resolve. Where the tsunami waves are loud, traceable events tied to specific solar eruptions, this newer signal is a subtler, ongoing texture in the plasma itself, a second layer of complexity in an environment that keeps turning out to be far more active than anyone predicted. Which brings us to why this discovery matters right now, in the summer of 2026, and not just as a historical footnote. Voyager 1 is still out there, still listening and still transmitting, but its power is running out. The spacecraft is powered by radioisotope thermoelectric generators that convert the heat from decaying plutonium into electricity, and that power supply has been shrinking by roughly 4 watts every year since launch in 1977. To manage the decline, NASA's engineering team has been switching off instruments permanently, one by one, to keep the spacecraft alive as long as possible. In April 2026, they shut down the low-energy charged particles instrument, one of the tools that helped confirm Voyager's original crossing into interstellar space nearly 14 years ago. But the team hasn't given up on getting more out of this aging spacecraft. Engineers have been testing an experimental power-saving procedure, internally nicknamed the Big Bang, designed to squeeze extra electrical capacity out of systems currently running below full efficiency. It was tested first on Voyager 2 in May and June of this year, and if those tests succeeded, the same procedure was scheduled to be attempted on Voyager 1 starting this month, July 2026, potentially bringing at least one shutdown instrument back online. And in just a few months, on November 18th, 2026, Voyager 1 will cross a distance of exactly 1 light day from Earth, about 16.1 billion miles, becoming the first human-made object in history to reach that distance while still alive and still transmitting. At that range, a signal traveling at the speed of light takes a full 24 hours to arrive, and another 24 hours for any reply to come back. Every one of those milestones matters because Voyager 1's plasma wave instrument is still running, still capable of catching the next tsunami wave whenever the sun sends one out and it eventually arrives. More than a year later, at whatever new stretch of interstellar space the spacecraft happens to be crossing. By then, as long as that instrument keeps working, humanity keeps its only direct, in-place method of listening to the space between the stars ring in response to our own sun's violence, from a vantage point no telescope on Earth, and no other spacecraft ever built, has ever occupied. There's a bigger reason this matters beyond pure curiosity, too. The same heliosphere that Voyager 1 left behind in 2012 is the bubble that shields Earth and every planet in our solar system from a significant share of the highest energy radiation drifting through the galaxy. Every tsunami wave Voyager 1 catches gives scientists a better, more precise picture of exactly how dense and reactive the material pressing against that shield from the outside actually is. That's not an abstract detail. It's part of understanding how stable our solar system's protection from the wider galaxy has been, and how it might change over long stretches of time. A question that starts, very literally, with a wave of pressure crossing 15 billion miles of dark space to ring against a single aging spacecraft's instruments. So the next time you look up at a clear night sky and think of it as still, silent, and empty, remember what Voyager 1 actually found out there. Something invisible, born in a solar eruption, crossed 15 billion miles of supposedly empty space and made the universe itself ring like a bell. It wasn't a planet. It wasn't an object at all. It was a wave moving through the dark, and one small, aging spacecraft happened to be listening when it finally arrived. And it's worth remembering that this wasn't a one-time fluke of good timing. It happened in 2013. It happened again in 2014. And somewhere out there right now, another coronal mass ejection, the sun released months or years ago, is still crossing that same stretch of darkness, closing in on wherever Voyager 1 happens to be at this exact moment, waiting for its turn to make the plasma ring one more time. If you want to hear about the next tsunami wave the moment scientists confirm it, subscribe and turn on notifications, because Voyager 1 is still out there, still catching signals nothing else in human history has ever detected, and the story isn't finished yet.